Nour-Dana Al-Abiri. Hello, my name is Nour-Dana Al-Abiri, and today I'm going to be presenting two of week 5's case connections. So starting with case 1. So we're going to start by talking about some of the normal mechanisms of ammonia transfer in the body and some of the processes that go on. So ammonia levels in the body are managed through the urea cycle in the liver and the actions of glutamate dehydrogenase, glutaminase, and glutamine synthase. Glutamate dehydrogenase catalyzes the reversible reaction between alpha-ketoglutarate and glutamate, leading to the oxidative deamination of glutamate to release ammonia. This process regulates the integration of carbohydrate and amino acid metabolism and nitrogen metabolism. Glutaminase converts glutamine to ammonia and glutamate to regulate ammonia levels, especially during metabolic stress or high protein intake. Glutamine synthase, on the other hand, catalyzes the synthesis of glutamine from ammonia and glutamate. This process incorporates ammonia into a non-toxic form that can be safely transported in the bloodstream to the kidneys or liver for further processing. And then the last one we're going to be talking about is transamination, which also plays a very significant role in the formation of non-toxic ammonia. During transamination, amino acids are transferred to alpha-ketoglutarate, leading to the formation of a new keto acid and glutamate. This process is important for removing the excess nitrogen from amino acids and the synthesis of non-essential amino acids. Transamination also plays a significant role in maintaining the balance of amino acids and the entry of nitrogen into the urea cycle, where it is converted into urea for extraction. So in the case that was described, the newborn has high ammonia levels, which could be caused by various dysfunctions. One of them could be a defect in the urea cycle. The newborn has genetic disorders that are affecting her enzymes in the urea cycle, leading to impaired ammonia detoxification, which increases the levels of ammonia in her blood. The second dysfunction is inadequate glutamine synthase. The newborn could be experiencing deficient glutamine synthase, leading to the body's inability to convert ammonia into glutamine, which could cause an increase in free ammonia levels. And therefore, it's important to consider the metabolic pathways in regulating ammonia levels and their potential dysfunctions in diagnosing and managing the newborn's condition effectively. Okay, so now to talk about how nitrogen transport is connected to gluconeogenesis in the fasted state. So we know that R-alanine and glutamine are the two non-toxic carriers of ammonia. So the transportation of nitrogen in the body is connected to gluconeogenesis in the fasted state through glutamine and alanine cycles. In the fasted state, the muscle protein is broken down and releasing amino acids. Transamination occurs to convert pyruvate and glutamate into alpha-ketoglutarate and alanine. The alanine is then released into the bloodstream and moved to the liver, where another transamination occurs to convert it back to pyruvate, which can enter gluconeogenesis, resulting in the production of glucose to maintain blood sugar levels. Glutamine also plays a vital role in transporting nitrogen in the fasted state. Glutamine is synthesized in peripheral tissues from ammonia and glutamate through glutamine synthase, leading to the detoxification of ammonia. Gluconeogenesis is also important for maintaining glucose homeostasis. The nitrogen transported by glutamine and alanine is vital in synthesizing new amino acids and other compounds containing nitrogen, which are needed for gluconeogenesis. Gluconeogenesis and nitrogen transportation ensure that the body can effectively manage nitrogen waste while producing the glucose needed in the body during the fasted state, leading to metabolic balance. Now to talk a little bit about the laboratory findings. So when looking at the laboratory findings, it suggests that the urea cycle enzyme that is most likely deficient in the newborn is ornithine transcarbamylase. The deficiency of ornithine transcarbamylase is characterized by the elevated levels of orotic acid because of carbamoyl phosphate accumulation, which is then transported to the pyrimidine biosynthetic pathway, resulting in the high production of orotic acid. The newborn also has an impaired urea cycle enzyme. The urea enzyme that is least likely to be impaired is arginase, and that's because the arginase enzyme impairment arises when the accumulation of arginine and its metabolism results in neurological symptoms, but orotic acid levels remain normal. In this case, the orotic acid levels are high, which indicates that there's no impairment of the arginase enzyme. The ornithine amino acid, though, we can conclude that the ornithine amino acid is essential in the ornithine transcarbamylase deficiency because it can help manage the metabolic dysfunctions in the OTC deficiency. So that's all for case one. Moving on to case two. We're going to start by talking a little bit about the metabolism and maturation of VLDL particles. So the information provided in the case scenario indicates that the patient has non-alcoholic fatty liver disease, and under normal conditions, very low density lipoprotein particles are produced in the liver. The VDL secretion and synthesis involves VLDL assembly, triglyceride synthesis, VLDL secretion, and apolipoprotein B100 synthesis. VLDL assembly includes assembling ApoB100 and triglycerides into nascent VLDL particles in the hepatocytes endoplasmic reticulum. Triglycerides synthesis involves the conversion of glucose and fatty acids into triglycerides through lipogenesis. VLDL secretion involves the secretion of mature VLDL particles into the bloodstream through exocytosis. Apolipoprotein B100 synthesis involves synthesizing ApoB100 through the liver. The maturation of VLDL involves triglyceride hydrolysis, interaction with lipoprotein lipase and apolipoprotein C2 activation. And in this interaction with lipoprotein lipase, the VLDL interacts with lipoprotein lipase on the capillary endothelial cell surface. The triglyceride hydrolysis involves the hydrolyzation of triglycerides in VLDL to release fatty acids. And then apolipoprotein C2 activation involves the transfer of apolipoprotein C2 from HDL to VLDL, leading to the activation of lipoprotein lipase and supporting triglyceride hydrolysis. The loss of triglycerides in VDL makes the VDL denser and smaller, leading to the formation of the intermediate density lipoprotein, or IDL. The IDL, intermediate density lipoprotein, is then carbolized by the hepatic lipase to form the low density lipoprotein, or LDL. The low-density lipoprotein is cleared from the bloodstream by the liver through low-density lipoprotein receptors, which attach to the ApoB100 on the low-density lipoprotein particles. So we're going to talk a little bit about the non-alcoholic fatty liver disease, or NAFLD. And its impaired processes that go along with it. So NAFLD could manifest through the risk factors mentioned in the case scenario. One of the risk factors is the accumulation of fat. So the primary manifestation of NAFLD is the excess accumulation of fat in the liver cells, which can be detected through an ultrasound. The second risk factor is the elevated liver enzymes. So the patient described in the case study has elevated liver enzymes, indicating that there might be liver damage or inflammation, and the patient could also be progressing to cirrhosis and non-alcoholic steatohepatitis, which is NASH. When NAFLD progresses to NASH, the patient is at elevated risk of developing liver cirrhosis and liver fibrosis, which can be categorized by the scarring of the liver tissue, which can result in complications such as hepatocellular carcinoma and liver failure. NAFLD could also be asymptomatic. In most cases, other symptoms can also include abdominal discomfort, fatigue, and signs of edema, ascites, and jaundice that can all develop over time as the disease progresses. The patient's condition in the case scenario can also be a result of impaired processes in NAFLD. So one of the processes that could have been impaired is lipid metabolism. In NAFLD, there's an imbalance between lipid synthase uptake and export, which can lead to increase in fatty acid in the liver, impaired fatty acid oxidation, and decreased lipoproteins export. The second impaired process that could be found is insulin absorption. Insulin resistance is a major factor in NAFLD development because it results in increased lipolysis in the adipose tissue, which could lead to an increase in free fatty acids in the liver. The patient could also be experiencing mitochondrial dysfunction. So impaired mitochondrial function can reduce the oxidation of fatty acid, leading to the accumulation of fat in the liver and the enhancement of oxidative stress. The patient's gut's microbiota composition could also be altered, leading to diabosis, which increases intestinal permeability, allowing the movement of bacteria products into the liver, which could also cause liver inflammation. Thank you.